Okay, so we'll talk a little about carriers and modulation, AM and FM, the modulation envelope, single sideband, some digital modulation techniques, the effect of overmodulation, and a little bit about a communications link, which doesn't seem to fit with the others, but that's where they stuck it. So we talked about amplitude modulation, where you're varying the amplitude of the carrier with the with the amplitude of the baseband signal or the modulating signal. And you do that with a mixer. Just a regular mixer or a balance mixer. You only need to use the balance mixer when you're trying to do single sideband because you want to get rid of the carrier. If you're doing frequency modulation, you're wanting to change the frequency of the carrier relative to the amplitude of the baseband signal. And also, you're actually changing the rate of the frequency change relative to the frequency of the modulating signal. Sort of like the acceleration effect of it. And for digital, okay, where we've got a 0 or 1 modulating, we're either going to change the frequency or we're going to change the phase, depending on whether we're doing frequency shift or phase shift keying. So we said amplitude modulation varies the instantaneous power level of the RF signal, and the modulation envelope is what you would get if you connect the peaks of that carrier. And that's what you get when you use an envelope detector. You recover that, which is just basically a rectifier. So what type of modulation varies the instantaneous power level of the RF signal? Delta. How'd they go back? Hadn't done that before. What's the modulation envelope of an AM signal? Alpha. Frequency modulation, it changes the instantaneous frequency in order to convey its information. So what's the name of the process that changes the instantaneous frequency of an RF wave to convey information? And those, in this case, the wrong answers are real things, just not the right thing. Phase modulation, we change the phase angle of the carrier RF signal. And we normally do that with a reactance modulator, which usually consists of a varactor, but there's some other techniques where you can vary the capacitance of the transistor or tube to do it. The thing that's always in the way? There's a way to make it disappear, and I forgot what it was. They're doing a binary phase. So it's like 0 or 180. You having trouble with the phase modulated signal? Yeah. Yeah. This one's easy compared to some of the others. It's hard to see. It's like trying to look at a single sideband modulation. What's the name of the process that changes the phase angle of an RF signal to convey information? What emission is produced by a reactance modulator connected to a transmitter RF amplifier stage? Now, if they had listed frequency, that would have been true too. Because you can change the frequency with a reactance modulator. In fact, it's kind of hard to understand the difference between changing the frequency and changing the phase. They're sort of connected. For single sideband, it's basically AM again, and we eliminate the carrier in one of the sidebands. It has the narrowest bandwidth, approximately, I think it's 2.43 kilohertz, something like that. It's probably on the next chart. You can get distortion called flat topping if you have an excessive drive or speech level. Like if your microphone gain is too high, you'll actually see clipping of the signal. So you're going to get harmonics because you've converted it into a square wave. And that's one of the things that ALC does also. If you're too high, ALC will try to limit it, which is essentially going to clip the signal. And it's especially a problem trying to get things set up to do like FT8. It does not like the ALC on. Which of the following phone emissions uses the narrowest bandwidth? Vestigial? Well, now that's real.
Maybe.
Sometimes I think it's in TV. They'll leave a small vestigial sideband. It makes it easier to discriminate or something. Because, I mean, sure, you know, single sideband is difficult to tune in because there's no reference. It's like, well, okay, this sounds good.
Sounds good to me, but may not sound as good to you.
Gotta listen to a lot of Donald Duck cartoons, and then you're.
Yeah.
Yeah, I'm never sure which way to go when I get the rain barrel or the Donald Duck.
Yeah.
What is meant by the term flat topping when referring to a single sideband phone transmission? Okay, digital modulation. In this case, we're going to do frequency shift keying. Okay. And in this case, it could be FT4.
Say 4 in 4 and 8.
Because 8 has 8 states and 4 has 4 states.
4 states.
FT4 sends 2 bits as a symbol. FT8 sends 3 bits as a symbol. There's 8 tones that represent a 3-bit symbol. FT4, it says 4 tones. That's why it's called FT4. I don't know if this was meant to be FT4, but that's what FT4 would look like. And it is frequent, it's audio frequency shift keying.
So those are 2 bits at the top.
Yes. And you see they're going zero, well, they're kind of random. 0, 1, 2, and 3. So 4 different states.
Yeah.
So depending on which one determines what that frequency is for that symbol.
So if that were FT8, you'd have another digital signal.
You'd have a third blue line, a third blue symbol, yes.
Now you've got more different or more
Yeah.
frequency shifts.
But you still squeeze it into 50 hertz. So you divide 50 by 8 and you get 6.25 hertz per state. That's how much it changes by, which is hard to believe they can detect that. It's hard to believe FT8 works.
There's magic in somewhere. So maybe you're explaining a question that I've had from ever since I started FT4 and FT8 is why does FT4 disappear at a certain time?
I don't know.
It's the same frequency, almost the same frequency.
Yeah.
You're only,
Yeah. I don't think it's a propagation issue.
I think it's just people.
Yeah.
Well, that doesn't mean-
And I never actually found that many people doing FT4, although I didn't look that much.
I just
I love FT.
every now and then I just bring up FT4. If I worked everybody on that frequency today on FT8, then I go to FT4 and lo and behold, I'll see some of the same.
No, I go the other way, I work all FT4s, with fewer of them, and then have, it's a punishment to go to FT8.
You have a hard time with a lot of things.
I think, but FT8's twice as long,
Yeah. 15 seconds. Yeah, big deal.
well.
Well, 30.
we're talking Instant gratification here. But that all has to deal with either 2 or 3 bits that are being modulated.
Right.
Now,
FT8
that won a Nobel Prize, so don't think too hard.
What?
The guy who came up with it
Right.
won a Nobel.
Joe Taylor.
He got a Nobel
Yeah.
Prize? Okay.
Well, actually, this was a result of deep space network
Yeah.
transmission
So they came.
and sonar. Because one of the things they use in FT8, I assume FT4, I've never really looked into it, is called a Costas array. And they take, after they build the FT8 waveform, or bit form, I should say, they divide it in half and they stick a Costas array on the front, one in the middle, and one on the end, which is a specific pattern. You take a 7x7 square and put a 1 in every location such that there's only a 1 in a single row or a single column, which makes it a unique pattern. And that's kind of one of their sync things they use. Plus it has a lot of forward error correction added to it also. That's why it's like 3 times longer than it really needs to be if they were just sending the call sign and signal report.
Data correction or error correction, you increase the number of
Right.
digits.
Right.
But there's no error correction. in FT4.
Oh, yeah.
Yes, there is. Absolutely.
Yeah.
There is?
Yeah.
Yeah. And you'll never know if it corrected a bit here or there. It just does it automatically.
Oh, well, maybe that's why.
Yeah. It doesn't say it was.
Yeah, well, it doesn't tell you. I
It doesn't
mean,
tell you, yeah.
but if it doesn't correct it, then it kind of, I think it throws it away. You don't decode. Okay. So how is direct binary FSK modulation generated?
Like me.
Reconfigure your key.
Hmm. Now, C is interesting in the way they worded it, but the protocol, I don't think it's the protocol. But it actually, that's the interface that you change with normally if you're driving with a computer. Now, there's some radios that have basically compute power built in. They can do FT8 without an external computer. Okay, QPSK31. Okay, it's PSK31 with quadrature phase shift, where PSK31 by itself is binary, 1 and 0. This does 4 states. So you're changing and it's also phase shift as opposed to frequency like FT8. So you get a 45, a 135, a 225, or a 315 phase, depending on what the state of the 2 binary bits are. And it produces a waveform like the one shown because they use sinusoidal bit modification, something like, I forgot what it's called. I think it's on the next chart. As opposed to having a nice square, they use that sinusoidal or Gaussian modifier to round it off so you don't produce the equivalent of key clicks or harmonics. So what is QPSK modulation?
Delta.
I'm going to say delta.
Process of
Elimination.
I'm saying delta.
Well, let's go back because,
Different angles.
yeah, but they're showing at 0 to 45. The difference between these, okay, is 90 degrees. So it actually doesn't matter whether you start at 0 or 5 or 10, as long as they're 90-degree differences between them. Right. Which of the following is characteristic of QPSK31? I don't think I mentioned that.
I read it in all I could say.
Well, you wouldn't expect it to have the same bandwidth because you've got 4 bits as opposed to 2. Even though the symbol rate's the same, but it's going to be a little bit wider, I think. And that encoding itself does not generate any error correction. I think it's, oh, no. Okay, I guess it is close enough to the same one. What? Encoding provides error correction? Oh, I don't believe that.
Go to your previous slide.
Is the sequence of codes allowed something that automatically disallows certain invalid states and therefore can be used to detect errors or correct them? I don't know, I'm asking.
That's a good question. Yeah, it is on there. Forward error correction. I didn't mention that it was sideband sensitive. But I can't say I understand how it's forward error correction. Because there's no additional information there. It's on the chart, must be right. I'm sure I got that off the internet when I looked it up.
Well, there,
The only way that would be true is with the digital encoding at baseband.
That's right, Joe.
it is the same thing.
Yeah. I would expect it to be slightly larger. What do I know? Because it's phase shift where Carson's rule doesn't apply. I don't know what it is for phase. Well, I will look into that. But since it's a correct answer on the exam, it must be right. By the error correction, right? Because the people that make up these tests, I'm sure, never make a mistake. Okay, so digital modulation. One of the main packages is called WSJTX, which actually stands for Weak Signal. Joe Thomas, I think it's Joe. Dash X. So there were other versions.
Joe Taylor.
Taylor, excuse me, Joe Taylor. And some of his stuff was also, there was a guy named Frank, which is where the F comes in for some of these modes. It was Frank with an E, I believe. And like I said, it was a result of stuff they did doing deep space communications for probes and things. And also some stuff that they use with sonar for submarine communications, very low frequency stuff.
So did Joe, Taylor, did he develop stuff for NASA?
Mm-hmm.
And
In the
then
military.
adapted for ham radio?
Yeah. He got the Nobel Prize. He's Bell Labs. He got the Nobel Prize for deep space stuff. But he's also a ham. And so is Frank, I believe. So the two of them did a bunch of this stuff that's in WSJTX. And then there's JS8 call, which somebody else did, but it's based on the protocols and stuff that like FT8 uses. Whisper is also part of that package, which was, yeah, the Pico balloons send Whisper because it's essentially for beacons. So every, was it 30 seconds or minute, they would send out a burst.
Yeah, you set up the duty cycle.
Okay, so FT4, we talked about, uses 4 tones. FT8 uses 8 tones. And it's a 50 hertz bandwidth, so they divide that 50 hertz by 8 to get the frequency for each one of the frequency shift for each one of the tones. The next one is the technical definition. It's Gaussian filtered constant phase, constant amplitude, frequency shift keying. usually they call it, um, uh,
Smoke and mirror.
no, audio frequency shift keying. Because it is at audio frequencies. So what you're doing, you set, like for FT8, you might set it to 7074, and then you've got a approximately 3 kilohertz band. You're somewhere in there, so you're transmitting an offset and then that symbol. So you're varying at 50 hertz region out there at whatever the offset is. And if you run in split mode, do you use split mode? If you set it up for split mode, it will automatically offset another 500 hertz in order to keep the basic off. It changes your transmit frequency, so it always keeps your offset around 1,000 hertz to improve the signal to noise ratio. Because if you're out here, 3,000 hertz away, that is much harder for it to decode. So it actually works better in split mode. A 7300 works in split mode. Yeah, in the WSJTX or the FT8 setup, you can pick fake it, and that works the same way. It will automatically do that.
So BPSK 31 is a little bit narrower than FT8.
Actually, I thought BPSK 31 was 51 hertz.
31, that's what the 31.
Oh, 31 baud. Yeah.
Okay.
I think it's around 51, 52 hertz, but I could be wrong. I was wrong once.
Or somebody made a mistake.
Yeah. Okay. Whisper, weak signal packet reporter. It's basically used for beacons, and there's beacons all over the world that send out their little call sign and stuff. And essentially, it's for propagation detection. If you can detect a beacon that time of day on that frequency, then it means the propagation between you and where the beacon is pretty good, because they're very low power transmitters. And there's WhisperNet, where you can go and see the reception reports for all of those. So what type of modulation is used by FT8? You didn't have to guess at that one, did you?
I'm a little prone to go to the paper there.
Oh. Yeah, okay. Now we hadn't got the vestigial sideband yet. Okay. Overmodulation, which means you're modulating more than 100%. And what that does to the waveform, you see a standard amplitude modulation waveform where you're undermodulating, which means you're not going to get as much power out. And down here at the very bottom, you're 50% over, 150%. And it really creates a bunch of harmonics, and you see this little extra envelope there, so you kind of doubling the frequency. You're giving me a blank look.
Well, I'm looking at that.
Resting confused states.
So all this energy down here is going to be, you notice there's your envelope now has twice the frequency, even though it's fairly low amplitude. So that's going to be a second harmonic. So what you want is 100% modulation to get the maximum amount of power. If you're doing it, and that was AM, if you overmodulate in FM, then your deviation is greater, so you wind up getting a much wider bandwidth than you would. And let's see. Oh, they're listing some common FM peak deviations of plus or minus 75 kilohertz and plus or minus 5 and plus or minus 2.5. I'm not sure why I care. Those are there.
It's in red, so.
Yeah, it's in red. I wonder why I put it in red. I don't think there's a question. Which of the following is an effect of overmodulation? Delta.
Now they're assuming FM there?
Yes.
Okay.
I guess it would affect the bandwidth a little on AM if you're, got that second harmonic in there. But I think the point of that one was just for FM. Communications link. When you set up to try to communicate from point A to point B, like I guess the best example is if you're trying to do something like moon bounce, where you really care about this stuff. There's two things you look at, the link margin and the link budget. And the link margin is the difference between the received power level and the minimum required signal level at the input to the receiver. So we talked about, I think last week, the minimum discernible signal level on your receiver. So whatever that is, and you probably need to pad it a little bit to actually be able to not only have recognize the signal, but be able to hear it. So whatever that level is, the difference between that and the power of the received signal that you got is going to be your link margin. So if, let's say, your minimum level was minus 100 dB. If your received power was minus 90, then you got a 10 dB margin.
Where do these numbers come from?
I just made it up.
Well, I mean, in real life, if you're.
Well,
apparently
your
that's-
noise floor on your receiver is minus 130, 120, something like that, probably. And a lot of these weak signals are going to be down there minus 90, minus 100.
Close to that noise.
Yeah. But if you're 10 dB above it, that's a 10 dB noise figure. But that's how they figure the link margin.
So it's just the difference between.
Which means, you're communicating and you've got a margin of 10 dB because the signal is not going to be constant. So due to propagation and stuff, and you may average minus 90, But it may go down to minus 95. Now it's only 5 dB difference. So that margin is basically how much extra you have, or headroom, I guess is one way to call it. Whoops. Whoops.
Problem.
So what is link margin? You didn't see that slide. Huh? You believe it's Baker, okay? So we also have a link budget, which is like figuring the entire path. So you add up all the gains and losses in the system. So you take the transmit power. In essence, you're going to do the effective radiated power, because you take your transmit power, the antenna gain, the path loss. In the case of going to the moon and back, it's like it's 251 dB, I believe. That's a lot of loss. Then you have your receive antenna gain. If you're doing something like moon bounce, you probably have a preamplifier up there on the antenna. You have cable loss between the antenna and your receiver. And then you have the receiver sensitivity. So you add all that up and you can determine the link margin from that. Because now you know what the power, the calculated power that you're expecting to receive and what your receiver requires. So if all that stuff added up to minus 90 and you only need minus 100, and you're back to your 10 dB margin. Did I confuse you too much? Okay. Well, just remember this line here. It's receive power, okay, is the transmit power plus the antenna gains, transmit and receive, minus the losses. So what is a link budget? Think it's Charles? Yeah. B didn't quite do it because they left out what?
System.
They left out transmit power.
Oh, there's system, okay.
Okay, so we talked about all this good stuff. Was there any questions on any of those? Well, I mean, ask it now. I don't want to go through all these if we don't need to. I don't want to be here 5 hours again.